Okay, so let's summarize a little bit. I guess in a few minutes here, I'd like to kind of draw your attention for what the main takeaways are, right? What should you take away from this lecture, and maybe what should you rewatch if you're not entirely comfortable with a particular idea. And we started with this notion that typically in the sciences or in engineering applications, you're often stuck with the problem of translating plain words into mathematics, right? And sometimes it's difficult, sometimes it's easy, and we certainly saw an example of it, right, by describing how this urn operated, right, how these particles of gas move between the two chambers. In words, we quickly arrived at sort of a mathematical description, and that necessarily called upon the notion of random variables, stochastic processes, distributions, expectations, right? All of these concepts in probability came up immediately, and hopefully you're comfortable with now explaining why xk, which is the number of particles in the left urn at time k, is a random variable, right? So hopefully you can kind of pause the video here and say, yeah, here's why it's a random variable, right? And hopefully you're also clearly sort of understanding what a stochastic process is. No doubt you've seen them in 160A, but it's useful to just kind of say, what is it, right? And all it is it's a collection of random variables. If we established that xk was a random variable and we took a sequence of them, right, here the sequence is indexed by this discrete time, and we'll see continuous time stochastic processes as well, but here we have a discrete time stochastic process, and what is it? Just a collection of random variables, right, indexed by time. The notion of distributions and expectations came up. We saw that the distribution for xk was sort of, quickly growing to be unmanageable for larger values of k, and we kind of had trouble in many ways calculating the distribution of xk for an arbitrary value of the time. But and that immediately brought up this notion of first transition analysis, right? This is really kind of a major tool in a setting of Markov chains that allows you to compute expectations of these chains at any point in time without getting the full distribution, right? That's sort of the key takeaway here, is that we never really ended up computing the distribution of xk to get the expectation, right? This is sort of this approach allowed us to bypass all that, and you'll get plenty of practice in homework 1 with this type of approach. And so, and the last point here, right, is we kind of took this fun detour into physics, and the point there was just to show you how some of these abstract notions of sample space and the state space, like why do they come up, and why do we need them? How are they motivated in the context of real problems? And in this case, in this physics problem, namely the Ehrenfest urn, we saw that sample spaces correspond to microstates and state spaces correspond to macrostates, and so these definitions kind of had this extra motivating value, right? So you could see something more tangible rather than just abstract sort of mathematical definitions. Let's see if there's anything else here I'd like to say. So not so much, other than hopefully you kind of learned a little bit of history of this model, right? It's a fun example, and I've so far each of the 2 times that I've taught the course, I've started with this model. It's a kind of a favorite of mine, and with all this rich history and all these connections to entropy, the second law of thermodynamics, perpetual machines, quantum computing, and all these things we discussed here, hopefully you have some of this terminology and can go ahead on your own and maybe explore some of these topics by yourself. So until the next lecture, I'm signing off, and see you then.